Okay, let's talk about the last method for drawing internal forces diagrams for indeterminate structures. The first method was superposition, and then the second method was called three-moment equation, and then virtual work, and then the last method is called moment distribution. From the name of the method, there will be a moment and it will be distributed. Okay? It's called moment distribution. Okay? Before we go through any example, first we have to go through important definitions in order to better understand the steps of solving any example. Okay? First definition, before the first definition, we know an equation that F equal K times delta, or K equal F divided by delta. What is K? K is stiffness and F is the force and delta is displacement. I think you saw this equation before. It might be different symbols, like delta, you might saw it like this. Force, you might saw it P, like this. So P equal K times delta, F equal K times delta, or K, the stiffness, is the force divided by displacement. This is the main equation that we will use to understand the steps of solving the example. From this equation, if delta equals to 1 unit displacement, so what will be the value of the stiffness? It will be the same value of the force, right? So, what kind of forces do we have? It might be horizontal force, might be vertical force, and it might be moment. Moment is kind of force, okay? So the three kinds of forces: horizontal force, vertical force, and a moment, okay? So if this is in a case, it is a moment. The force is a moment. So it will be called rotational stiffness. Rotational stiffness. If I want to calculate the rotational stiffness, that means that the F is a moment and the delta is a rotation. So here in this equation, F might be horizontal force, might be vertical force, might be moment. What about delta and the displacement? It might be horizontal displacement, it might be a vertical displacement, and it also might be a rotation. If I want to define the rotational stiffness specifically, so I mean here that F will be a moment and the delta will be a rotation, okay? So the rotational stiffness, if I need to define it, it will be the moment needed to produce a unit rotation. The moment needed to produce a unit rotation. If I need to define the translational stiffness, the word translation means displacement if it's horizontal or vertical, not a rotation. Translational stiffness means the force, not the moment here, the force needed to produce a unit displacement. Or in other words, it's the force needed or the force produced from a unit displacement, or the rotational stiffness, the moment needed to produce a unit rotation. In all the meanings, when the delta equals 1, so that stiffness will be the force. Okay? Let's talk about the rotational stiffness. This is the most important one I need to talk about. Again, what's the definition of the rotational stiffness? It's the moment needed or the moment produced due to a unit rotation. So if I need to calculate, this is a beam, a fixed beam, or a fixed member. And at a unit rotation took place. So there is, you remember the yielding of supports? It's the same. As I told you, there is a unit rotation here, or a rotation happened that equals to 1, a unit rotation. Please calculate the reaction. So it's like a superposition example. No loads. Only I am asking you to calculate the reaction due to a unit rotation. These reactions will be equal to, if we use the superposition method, will be equal to 4EI divided by L, and the other one will be 2EI divided by L. And EI is the inertia for this member, and L is the member length. Okay? And the direction of both of these reactions, the MA and the MB, will be the same direction of the rotation that happened. This rotation is anti-clockwise, so both of the two reactions or the two moments will be anti-clockwise. The one closest to the point that the rotation took place at will be 4EI over L, the biggest value, and the other side will be half of it, 2EI over L. You have now to recognize these two values. If you need to double check where did I get these values from, as I told you, it's a superposition example, as simple as no loads, and there is a yielding of support that happened. Rotation at A equals to 1. Calculate the reactions. Case node, no case node, no loads. Case 1, and then delta 1 or theta 1 node plus theta 1 1 will be equals to 1, not 0, because there is a yielding of support. At the end, the reactions will be 4EI divided by L at the side that the rotation took place at, and the other side will be 2EI over L. You have to recognize these two values. Okay? The third definition I need is called the carry-over moment. I give it the abbreviation COM, carry-over moment. What's the carry-over moment? If you have a member, a beam, no loads, and there is a moment, an external moment at A, not the reaction. I am talking now about an external moment like 10 ton-meter, 6 ton-meter, whatever the value. What will be the final reaction here? What will be the final reaction? No loads, only an external moment at A, M is, as I'm telling you, 6 ton-meter, 10, 4, whatever. What will be the final reaction at the other side? You can do it as a superposition example. It's indeterminate structure, main system, and whatever. What will be the final reaction here? The final reaction here will be M over 2 in the same direction. M over 2 on the same direction. The fourth important definition here is the joint stiffness. If I have a joint here like this, and 3 members are partners in this joint. So I have a joint called A and three members AB, AC, and AD. What will be the joint stiffness? Here I was talking about the stiffness of a member. I'm here talking about the stiffness of a joint, of a point. Okay? So the stiffness of the joint is a summation of the stiffnesses of any member partner in this joint. So what are the members that are partners in this joint? AB, AD, and AC. So if I want to calculate the stiffness of the joint A, it will be the summation of the stiffnesses for all the partners at A. So it will be the stiffness of the member AB plus the stiffness of the other member AC plus the stiffness of the third partner, which is AD. And take care, KAB is not like or not the same as KBA. They are totally different. They might be at some point the same, but not all the time. So take care. You are talking about the joint A, so the members or the partners of this joint will start with letter A. So this member will be AB, AC, and AD. The fifth important definition here is called the distribution factor. DF, distribution factor. Here I am asking you a question. If I have a moment of 10 ton-meter on the joint A, how will be the 10 ton-meter, this moment, how will it be distributed on the three partners of the joint, AB, AC, and AD? What will be the main factor that's affecting this distribution? The main factor that will affect the distribution is the stiffness of each member. If the stiffness of AB is the biggest among all the other two partners, so it will absorb the most of the moment in the meter. Let's say, if the stiffness of AB is 2, when I calculate 4EI divided by L, the answer is 2. And the stiffness of AD is 1, and the stiffness of AC is 1. So AB will take how much from the 10 ton-meter? AB, the stiffness was 2, right? What was the summation of the stiffness of the three members? 2, 1, and 1. So the summation is 4, right? So this member will absorb 2 over 4 from the 10 ton-meter, which is half the 10 ton-meter. What about this member? It will absorb 1, its stiffness was 1, divided by 4, the stiffness of the joint, which is the summation of the stiffnesses of all the partners, of the 10. So quarter of the 10, 2.5. And the same for AC, 1 divided by 4 of the 10, 2.5. So the distribution factor of any member is the stiffness of this member divided by the summation of the stiffnesses of all the partner members at the same joint. Okay? Let's talk about the last definition, which is called fixed end moment. We will always use FEM to talk about this. Let's talk about the last definition we need to solve the example, which is called fixed end moment. It's called in general fixed end force, but we will only use the term moment for these forces. Fixed end moment. What's the fixed end moment? I will be having like an example like this, a frame with a lot of members, And each member is loaded with different load, like it might be loaded with a uniform load, with a concentrated load in the middle, concentrated load which is not in the middle, any load. The fixed moment that I am making an assumption that each member is by itself, not connected with the whole frame, is by itself, okay? With the load, with its load, okay? And I need to calculate the final reactions, the final moments for both ends. This is called fixed end moments. How will I do this? Superposition. I have a fixed beam with a uniform load. Please calculate the final reaction, the final moment. If I'm talking about fixed end forces, it will be X, Y, M at A and X, Y, M at B, right? But I don't need the fixed end force, as I just told you. I just need the fixed end moment. You will not use a superposition for each member, for each load to calculate the final reaction. I'll tell you now what will be the final moment for each case. For this case, it will be PL squared divided by 12. PL squared divided by 12. What is P? P is the intensity of the distributed load. L is the member length. What about the second moment, and what about the direction of both moments? The second moment will be the same, PL squared over 12. Why will it be the same? Because the load is symmetric. The load is symmetric. So both moments make sense that they are equal. What about the direction? They have to be on the opposite direction because it is symmetrical. If this is in the clockwise direction, so the other one has to be the anti-clockwise to be symmetric, right? So the last question will be why they are like this with the tails upwards, not on the other direction with the tails downwards, okay? The answer for this question will be they will be the same direction as the load. If the load is from up to down, so the moments will be like this, okay? PL squared divided by 12. What if it's a concentrated load in the middle? What will be the final moment here and there? They will be the same as well, because again, this load is symmetric, and it will be PL divided by 8. What about the last case? Is it a symmetrical load? No. So for sure, this moment will be different than this one. Okay? This moment, now the P is not in the middle, so the distance from here is A, from the other side is B. This one will be the force multiplied by the closest distance, which is A, multiplied by the far distance squared divided by L squared. The same meaning. What will be the value of the other moment? It will be P, the closest distance here is B, the far one is A squared divided by L squared. All of this if the member, both ends were fixed. What about if one of the ends is hinged? What will this affect these values? And an important thing now, the fixed here, it doesn't mean a fixation, the fixed support, no. If I'm talking about this frame, that's called A, B, C, D, okay? The kind of the ends of any member Who will decide it is fixed from both ends, or it has one end which is fixed and the other end is hinged? Is what about the movement of the both ends? Is the moment known or unknown? If the moment is known, so that means I will put a hinged support. If the moment is unknown, that means that it will be modeled as a fixed support. Because you know the fixed unknown moment and the hinged is a known moment. So when I am trying to model an end that has a known moment, so I will model it as a hinged support. If I'm trying to model an end which has an unknown moment, I don't know the value, so it will be modeled as a fixed support for this frame. What about the member AC? Will it be fixed or fixed hinged? The answer will be, do you know the moment at A? Yes, it's a hinged support, so it's 0, I know it. What about the moment at C? Do you know it? No, it's an internal joint, I don't know what will be the value of the moment here. So this member AC, I know the moment from one end, and the other end I don't know the moment, right? So it will be modeled as a fixed hinge. What about the member CD? Do I know the moment at C? No, it's unknown. I don't know the reactions, I don't know. Do I know the moment at D? Also, I don't know. So how will be the member CD modeled? It will be fixed. You got it now? So fixed here, it doesn't mean a fixed support, a fixation. It means that this end, I don't know the moment at this end. And the hinged support means that I know the moment at this end. Again, the hinged means I know the moment, it's not a must, the moment has to be 0. If I just know the moment, even if it's a value like -2, I know it. So it will be modeled as a hinged support. So the hinged support here, not only if the moment is 0, no. If the moment is known, it will be modeled as a hinged support. Okay? So what will be the difference between the fixed, the member that both ends are fixed, and the other member that both ends, one is fixed and the other is hinged? The main difference will be that these members will only have movement on one side. Does the hinged support have a moment? No? Right? So the main difference between the fixed member and the fixed hinged member, that the fixed hinged member will have only moment on the fixed end. This is the first difference. But what will be the value? Please look here to know what will be the value. Okay, don't look here. I have another idea. In order to know the value of this one, assume that both ends are fixed. So when you see a fixed hinged member and you need to know the fixed end moment on the fixed end, assume that the member is fixed. What will be the moment here and there? PL squared divided by 12 and PL squared divided by 12. Right? I'm making it dotted because it's not really one. Okay? That's why I am making it dotted. But this end can't hold the moment. It's a hinged end. So where will this moment go? It will go, half of it will go to the other side on the opposite direction. Half of it will go to the other side on the opposite direction. What's the half? It's like this definition. When a member has a moment at one end, what will be the effect of this moment? That half of this moment will go to the other end. But here, it was in the same direction, right? Why here I am telling you half of this will go on the other side on the opposite direction? Why here it was the same direction and here it is the opposite direction? Before I tell you why, so this PL square over 12 will have another half PL square over 12, right? So the final value here will be 1.5 PL square divided 12. And you can recognize this by 1.5 PL square over 12. So if it's fixed, it will be PL square over 12 at both ends. If it's fixed hinged, only one moment on the fixed end, and it will be equal to 1.5 PL square over 12. But you understand what is the 1.5? Where did it come from, right? It's the PL square over 12, and then I made an assumption that the other end is fixed, and then I removed the moment because it's a hinged end. When I remove the moment, I have to take the effect before I remove it. What is the effect? That it has to give the other end half of the moment. So PL square over 12 coming from the other side, half PL square over 12. So that's why it is 1.5 PL square over 12. That's the clarification of the 1.5. The other clarification, why it's here, was on the same direction, and why here it went on the opposite direction. The answer will be as simple as, what is the difference between the action and the reaction? Do you know the difference between action and reaction? The reaction is the reaction. Reaction. What is the action? The action is the load itself. When I have a frame like this, these are called reactions, right? And any load is called an action. That's why the reaction is called reaction. It's two words. Reaction. It's for the action that happened. That's why it's called reaction. You saw that it's one word. No, it's not one word. It's reaction. The load itself is the action that's happening on the structure, and this on the supports. They have to resist this load. They have to resist this action. So that's why in the supports we call it reaction. Okay? Here, this was an external moment, right? So it's an action. But what about this? It was a reaction, right? The fixed moment is a reaction. So that's why this was an action and this was a reaction. So when I am talking about both of them, they have to be the opposite. If this one was on the same direction, if I was talking about an action, so if I am talking about a reaction, it has to be the opposite. So here it was the same direction, so that's why here it was on the other direction. What about this? This one will be 1.5 PL divided by 8. The same meaning. But what about this? How much will be? Is it 1.5 as well? You understood where did I get the 0.5, right? Because there is a moment here and the same moment on the other side, and this moment, half of it was transferred to this end. That's why it's 1.5. So you will not see the 1.5, you will see it only on the symmetric loads, right? Because both of them are the same. But when it comes with an unsymmetrical load, I have no rule for here. I have to calculate this. That's P A B squared divided by L squared, and I have to calculate this, which is P B A squared divided by L squared. And let's say this is like 16 and this is 8. Any numbers? Okay. So this will be 16, and then half the 8, which is 4, on the opposite direction. So the addition of the summation will be 20. So there will not be a rule for the unsymmetrical law. You have to calculate it from the proof that you understood from the symmetrical law. Okay, here's the frame. He's asking me to draw bending moment diagram using the moment distribution method. What will be the steps? Now I can talk with you about the steps because you already know the important definitions we talked already about. The first step. Calculate the rotational stiffness, which is called K. Please take care here. I have two types of examples. The first type, I will look at the frame. Is the part A, B, C, F allowed to move horizontally? Is the part A, B, C, F allowed to move horizontally or not? If there is any support that has any horizontal reaction, that means that the horizontal displacement is not allowed. You know that the reaction doesn't allow the displacement at its direction. That means if this floor has any horizontal reaction, that means that the horizontal displacement for the whole floor is not allowed. This is called non-sway. If the frame or the structure is going to move horizontally, like this frame, is anything at CD that has a horizontal reaction? Nothing. So that means that the horizontal displacement for the whole floor CD is allowed. So this frame will move like this. This will be C dash and this will be D dash. It will move either in this direction or the other direction. This is called sway. And we will exclude this type from our course, the sway structures, okay? We will only talk about non-sway structures. But just to let you know, if I have a frame like this, is it sway or non-sway? I have a hinge and support here, so I have a horizontal reaction here, so the horizontal displacement is not allowed. So this is non-sway. What about this frame? There is a spring here. Spring, superposition, spring. Can you remember spring? And K, the stiffness of the spring is infinity. What does stiffness of infinity mean? That it's very stiff. That means that it's not allowed to move horizontally. So you can see this, or you can see this, or you can see a fixed support at this floor. All of this have the same meaning, that this floor is not allowed to move horizontally. Other words, it's non-sway. Okay? For both types of structures, the sway and the non-sway, the first step, we are assuming that all the deformations are neglected. Even I am sure that there is deformation here. Even when I am solving this example, I will make an assumption that the deformations are neglected. I will only assume that the rotation is allowed, not the horizontal or the vertical displacement. That's why when we talked about the stiffnesses in the definitions, I stressed only on the rotational stiffness. I just passed through the translational stiffness. We will not use it. We will always calculate the rotational stiffness. Even there is a sway and all the displacements are allowed, we make an assumption that the horizontal and the vertical deformations are neglected, only the rotation is allowed. That's why we are defining and using only the rotational stiffness. Okay, let's forget about this. Let's go back to our example. So the first step, I will calculate the rotational stiffness for which members? For which members? I will calculate the rotational stiffness. Take care for a moment. The definition I will say now. I will calculate the rotational stiffness for the members that's going out from any internal joint that has an unknown moment. Again, where are the internal joints in this frame? B and C. What about the moment at B? Is it known or unknown? Unknown. I don't know the moment at B. What about the moment at C? Is it known or unknown? I know only one direction, that is 9 times 2 for the CF. That means that the whole joint C, I know the moment at? No. So the internal joints I have here are B and C, and both of them have unknown moment. So I will start for joint B and then go to joint C and calculate the K for any member that's going out from this joint. What are the members that are going from the joint B? The first one is BA, BA. And the second one is BD. The third one is BC. I will calculate the rotational stiffness for these three members. What about the joint C? I will calculate the stiffness of the first member, that is CE, and then CB, and I will not calculate the stiffness for CF. Why? Because it is a determinate part. I got bored from repeating this note from the beginning of the course. I think we dealt with this determinant part the same in the superposition and the three-moment equation and the virtual order and the moment distribution. If there is any determinate part, that I know the moment at this part, so I exclude it, because I am here talking about indeterminate structure. This is a structure 2 course. Okay? So CF will not be included here in this step. Okay? What about BA? Is it fixed or fixed hinged? BA is fixed. Both ends of AB have unknown moment. The rotational stiffness of the fixed member, can you remember it? It was 4 EI over L, right? So 4, only the inertia factor. So what's the inertia factor for BA? 6. For 4 times 6 divided by the L, which is 12. So 24 divided 12 is 2. That means that in this step I am not calculating the real value of the rotational stiffness, right? It's not the real value. If I need the real value of the rotational stiffness, it has to be 4 times 6 EI divided by 12, and the I will be a value like 10,000 10 meters squared. I'm taking only the inertia factor. So 2 is not the real value of the rotational stiffness. Stiffness is a big number, right? So it's only without the value of the EI. Okay? What about BD? Is it fixed or fixed hinged? It's fixed as well, right? So 4 I is 3 divided by L is 6, which is 2. What is the kind of the member BC? Fixed. The moment at B is unknown, the moment at C is unknown. So 4 times 6 inertia factor divided by 6, which is 4. Right? Please calculate sigma k here, which is the k of the joint. You know that the k of the joint is the sigma k of the members going out from this joint, right? It was a definition we talked about. Sigma k here is 2 and 4, which is 8, right? What about the other joint? KCE. What is the kind of CE? It's fixed, hinged, because the E is hinged? No, not because the and at E is hinged. Because at E, the moment is known whether it's 0 or other value. Okay? And the moment at C is unknown. So that's why CE is fixed, hinged. What will be the stiffness of the fixed hinged member? The fixed was 4 EI over L, right? What will be the stiffness of the fixed hinge? Can anyone tell me? Can you remember this diagram? If there is a theta here equal 1, right? So here it was 4 EI divided L, right? And here it is 2 in the same direction, EI divided L. That if this was fixed. What this, if this was fixed hinge? What will be the difference? Can anyone tell me? Rough. 2 EI over L, it's not allowed now, it's a hinged end, it's not allowed. So I have to move half of this moment to the other side. Oh, in the same direction or in the opposite direction? Opposite direction or the same direction? Opposite direction. So it will be like this. So it's half of the 2 EI divided L, which is EI over L, right? So this will be 3 EI over L. You are not asked for this proof. I'm just brainstorming with you, okay? I want to make you understand everything. Not to tell you the K of the fixed is 4 EI over L. You have to know why it's 4 EI over L. And the stiffness of the fixed hinge is 3 EI over L instead of 4. You have to understand why it is 3. But at the end, you will decide you want to understand or not. At the end, the fixed is 4 EI over L and the fixed hinge is 3 EI over L. Okay? But I just need you to understand. So this is a fixed hinged member, so the stiffness will be 3. Inertia factor is 2 divided by L is 6, so it's 1. CD is fixed, so 4 times 6 divided 6, which is 4. So what about the sigma k, Kc, which is sigma k? It's 1 plus 4 equals 5. Right? Second step will be distribution factor. EF. Which members will I calculate the distribution factor for? You don't have to think about it. the same members that you calculated the rotational stiffness for, you have to calculate without thinking and internal joints, known moment, unknown moment. No. The same members here, you have to calculate the distribution factor for that. Okay? So you need here to calculate the distribution factor for BA and for BD and for BC without thinking about it. Okay? And here you need to calculate the distribution factor for CE and CD. Okay? What's the definition of the distribution factor? It's the stiffness of the member divided by the stiffness of the joint. Right? So the stiffness of the member is 2 divided by the stiffness of the joint, or the summation of the stiffnesses, which is 8. So the distribution factor here will be 0.25. Here the distribution factor of BD will be 2 divided by 8, which is what? 0.25. The third one will be 4 divided by 8, which is 0.5. You have to make sure that the summation of the distribution factors for the members of the same joint has to be 1. Right? Because on other examples, this is not like straightforward like this 0.25, 0.5. It's like 0.2327. So you will approximate right 0.23. And the same for here. And the same for the third partner. So you have to check, to double check at the end that the summation of the distribution factors for the members of the same joint has to be equal to a whole 1. Okay? The same for the CE, it will be 1/5, which is 0.2. And here it will be 4/5, which is 0.8. The third step will be the fixed and move. You have to deal with each member individually. So A, B, you will take it out like this. Has 2 loads, 9 and 9. And BC will be like this. And it has a uniform distributed load, 4 tons per meter. And BD here, it doesn't have any loads. And CE as well doesn't have any loads. And here you will take the CF. And you know, no fixed moment, you know that it has a moment here, which is 9 times 2, which is 18. Okay? So we will exclude it in the main steps of the solution of the example. And the fourth step is the table, as we will talk about right now. So no CF in the main steps of the example. Even in the table now we will not include CF, but we have to only include it. Can you remember when I talk about the determined part? I always tell you remove it or throw it away, but before you throw it, you have to take its effect, right? So the effect here that it will be a partner with other 2 joints and it has a moment. This is the effect here, okay? What about the fixed and the moment for BC? BD doesn't have any fixed in the moment because it doesn't have any load. CE doesn't have any fixed in the moment because it doesn't have any load. So I have BC that has fixed in the moment here, and the same one is here. What's the value of the fixed in the moment when it comes to a uniform distributed load? It's PL squared divided by 12. So 4L is 6 squared divided by 12, which is 12, I think. And this one will be 12 as well. Right? What about this? We didn't say this before. We know the distributed load, the concentrated load in the middle, and the concentrated load that is not in the middle, right? This has two concentrated loads. How can I deal with it? How can I deal with this? It will be equal to this one and plus this one, right? And you know how to deal with this, and you know how to deal with this, right? That means if you have any load, even like this, and the concentrated load in the middle, how will you deal with it? The uniform load plus the concentrated load. So you can use this criteria in any other load. Okay? Let's remember how to deal with this one. This is not a symmetrical load, so this one will be different than this one, right? What is the value of this one? It's a load, 9, multiplied by the closest distance, which is 4, multiplied by the far distance, which is 8, squared, divided by L squared, which is 12 squared. What about this? It will be 9, the closest distance is 8, the far distance is 4 squared, divided by L squared, which is 12 squared. This?
Yes.
How much?
192.
192? 192? Impossible.
12 square?
Hmm?
12 square?
Yeah, 12 squared. So 192 divided 12.
So it's
192 plus 16. 192 8. 16. And what about this one? Huh?
96.
I think it's 8.
Yes.
I don't need anything from you.
806.
8, right? Right?
Yeah.
You double check the 8?
Yes, 8.
Okay. And what about this one? I think they will be the same, right? No need to recalculate it. But this one will be 16, and the other one will be 8, right? So what will be the total? 16 and 8 is 24, and 16 and 8 is 24. Yes, I know that they will be the same at the end, because this is a symmetrical load. So the both fixed and the moment has to be the same. This is 24, and the other one is 20. Right? Okay? What about the next step? The next step will be the last step. The last step. Okay, the last step is the table. The last step, number 4, is the table. The first row is the joint. The second row is the members from these joints, and then distribution factor, and then the fixed and the moment. Okay? Which joints will be included in the table? This is a very important question. Which joints will be included in the table? All the joints has to be included in the table except any joint that I have or I know the moment at it. The target of the table, at the end, I need to know the moment to draw the bending moment diagram. So any joint, any point that I know the value of the moment, what's the idea to include it in the table? So how many points I have here? A, B, C, D, E, F. Which of these 6 joints will be included in the table? A will be included, yes, because I don't or I need to know the moment at A. B will be included, yes, because I need to know the moment at B. C, yes. D, yes. E, I know the moment at E it's 0. So it will not be included in the table. F, I know the moment at F it's 0. So it will not be included in the table. So how many joints in this example will be included in the table? 4 joints. A, B, C, and D. Okay? A and B and B and C. Try to put the same distribution of the joints here in the table. I mean, if B is beside C in the example, try to put them beside each other in the table. It will be easier for you. Okay? A and B, they are beside each other. I couldn't. Okay, that's fine. What are the members of the joint A? It has only one member, which is called AB. You have to start with the name of the joint. The joint D, how many members? Only one member, which is DB. The joint B, it has BD, BA, and BC, right? Try to put the members beside each other. Which members? The members that have the same naming. AB and BA. BC and CB. Try as you can, okay? So when I'm trying here to put BD, BA, and BC, put BD here beside the DB, okay? And then BA, and then BC. Because when you put the members of C, put CB here beside BC, and then CE, and then CF. Distribution factor. Did I calculate the distribution factor for a member called AB? Did I calculate the distribution factor for a member called AB? No, I didn't. So the distribution factor will be 0. DB. Yes, DB. No, I didn't calculate. So DB is 0. BD. 0.25. BA 0.25 and BC 0.5. Right? CD 0.8, CE 0.2, CF I didn't, 0. Fixed and moment for AB. This is the fixed and moment. They are the only fixed and moment that I have, right? AB, 24, right? AB, so this one, 24. What about the signs? The clockwise is positive and the anti-clockwise negative. So this will be negative 24. Okay? I just need to double check each term, each semester. I put any signs I need. I change it every term. So for you, the sign will be okay, clockwise positive and anti-clockwise negative. That's fine. DB. Did I calculate any fixed in the moment for DB? I didn't. DB. This one. No, I didn't. 0. BD. BD. Nothing. 0. BA. This is BA. 24. Positive 24. Right? BC. BC. This one. 12. Positive or negative? Negative 12. CB, positive 12. CE, I did it 0. CF, it's 18. Positive or negative? Negative 18. Okay? What will be the second row? It's called distributed moment. So now, there is a moment and you will distribute it. Okay? How will I do that? Let's talk about the joint B. The joint B. I think it's supposed for any joint, the summation of the moment at any joint, it has to be equal to 0, right? What is the summation of the moment at the joint B? Let's calculate 0 and 24 and negative 12. So what's the summation? Positive 12. Is that right? No, because the fixed in the moment itself, it was an assumption. It's not right. That's why the summation of the moment at the joint B is not correct. What about the summation of the moment at joint C? 12, 0, and negative 18, which is negative 6. It's not 0. There's something wrong. Right? So now I have to fix something wrong that I did. The fix in the moment, it was an assumption. It's totally wrong. AB is not by itself. It's within a frame, within a structure. Right? How can I fix this mistake? Let's start with the joint B. What is the summation of the moments? Positive 12. And it has to be equal to 0. So I have to put a moment of negative 12. So the summation will be equal to 0. Right? If I put a moment of negative 12 above the joint B, how much will each partner B, D, B, A, and BC will get from the negative 12? Depends on the distribution factor. This will get 0.25 of the negative 12, which is negative 3. This will get 0.25 of the negative 12, which is negative 3, and this will get half, which is negative 6. Again, one more time for the joint C. What's the summation of the moment at C? 12, 0, negative 12, which is negative 6. Is that right? No. It has to be equal to 0. It's now negative 6. How can I fix this? I have to put a moment of positive 6, so the summation will be equal to 0. If there is a moment of positive 6 above the joint, how will it be distributed on the 3 partners? This one will get 0.8 solution factor of the positive 6, which will be positive 4.8. And this will get 0.2 of the positive 6, which is 1.2, and this will not get anything, 0. What about joint A and D? Don't think about them. The distribution factor is 0, so it will remain always 0. Okay? Again, now I put a moment from myself of negative 3 on the member BD, right? To fix the mistake. And I put another moment on the member BA of negative 3, and I put another moment on the member BC of negative 6 from myself, just to fix the mistake, right? What will this affect on the other members? There will be carry over moment. So the next row is carry over moment. Can you remember definition number 3? The carryover moment, if there's a moment at any end, it will be transferred to the other end by half and on the same direction. DD and DB. That's why I'm telling you to put the BD, DB, AB, and BC beside each other as much as you can. BC and CB. Is there any other ends of the same member? AB and BA, right? AB has 0, so it will not give any carryover moment for BA. But BA has a moment of -3, so it will give the AB a carryover of -1.5, half of the -3. Here 0 and here 1.5. Here it will be -3 and +2.4. Is there any EC in the table? No. Is there any FC in the table? No. So no carryover moment for C and CF. This is the carryover moment. We call this first cycle. It's a moment and then you distribute the moment. What is the moment that you are distributing? The fixed and the moment. This is called the second cycle. The carryover moment, and then you will repeat the same criteria again. You have to distribute it. Let's check the joint B. What's the moment? 0, 0, and 2.4. So the summation of the moment is 2.4. It has to be equal to 0. But I think it's getting better. In the first cycle it was 12, right? In the second cycle, it's 2.4. In the third cycle, it will be almost 0, right? So you are getting closer to the ideal value. The summation of the moments at any joint has to be equal to 0. So you have to make sure that every cycle, it's getting better and better, smaller and smaller, okay? So now, it's 2.4, so I have to bring a moment for myself, which is equal to -2.4 to make the summation equals to 0. So -2.4, how will the moment be distributed on the three partners depending on the distribution factor? Quarter of the -2.4, -0.6, -0.6, -1.2. Again here, see, the summation of the moment is -3. So I have to put a moment of +3 and then distribute it. So here point A, so +2.4, +0.6, 0. And again, carry over moment. And here, 0 and 0. Distribution factor are 0. Here it will be 0, -0.3. This is AB, BA was -0.6, so -0.3. 0, -0.6, +1.2, 0 and 0. And what will be the end? You have two options for when to stop the calculations. Either you will find the carryover moment, all the row of the carryover moment is 0. So that's it, stop. All the values are 0. From the second cycle, you might find them equal to 0. If not, so the right thing when to stop, when the moment, summation of the moment at each joint is equal to sharp 0. And this will not happen. Okay? Even after 1 million cycles. It will be 0.00003, 0.000. Okay? So we will make a deal. If not, the carryover moments from the second or the third cycles are all of them are equal to 0, just stop on the third cycle. So let's complete the third cycle and then stop as we decided. So here 0 and 0. The moment summation moment at B is 1.2. Make sure that it's getting better. 12, 2.4, 1.2. Okay, it's getting better and better. So the summation is positive 1.2. So I have to put a moment from myself of negative 1.2 to be summation of 0. Negative 1.2, so times the quarter, negative 0.3, negative 0.3, and negative 0.6. Here, it's getting better, yes, it was 6, and then 3, and then now it's 0.6. negative 0.6, so I have to put a moment of positive 0.6. This moment will be transferred to the three partners by the distribution factor, so this will be positive 12 and positive 0.48, and this will not get anything. And no carryover moment. Just the 3 cycles calculators. Now, the final moment will be the summation of all the moments. This is not a moment, this is a distribution factor, right? So you will have to make a summation of all the columns starting from the cell of the fixed and the moment. So this one, I am 100% sure that the final moment at C for the member CF, I'm 100% sure that it's 18, right? Yes, negative 18 and zeros. Yes, it is negative 18. If I made any mistake here, I'm 100% sure that it will be negative 18. So AB, each one like, huh? Negative 25.8. And DB, negative 1.8. And BD, negative 3.9, right? And BA, 20.1, right? 20.1. And then DC, 16.2. No, 16.2. Okay. Do you know how I knew that it's 16.2? The summation of the moment at any joint has to be equal to 0, right? So negative 3.9 and plus 20.1 and negative 16.2, the summation will be equal to 0. Okay? CD 16.08 positive, and CE 1.92, right? And negative 18, yes, I have to make sure that the summation of the moment at the same joint equals to 0. 16.08 and 1.98 positive, which will be equal to positive 18, and negative 18, yes, I am 100% sure that I am in the right place. Okay? How can I draw the bending moment diagram? You have to draw this one more time. The same thing when you draw each member, you make each member separate. You have to do this again. AB, and then BC, and then CF, and here B, D, and the column C, E. Okay? And then AB. AB is negative 25.8. What does the negative mean? Clockwise or anti-clockwise? Negative doesn't mean that it's an upwards movement. No. Negative and positive here from the table means our sign clockwise or anti-clockwise. So negative means anti-clockwise. So AB, this one, is anti-clockwise of 25.8. DB, this one, right? DB, so this one, it's negative 1.8. Negative also means anti-clockwise, like this, 1.8. BD, negative 3.9. BD, this one, negative 3.9. Negative 3.9, right? BA, positive 20.1. BA, this one, positive means clockwise. 20.1. BC, negative 16.2. BC, this one, negative 16.2. And CD, this one, positive 16.08. CF, I know from the beginning it's negative 18, 100%. CE, this one, CE, it's positive. Positive means clockwise, like this. How much? 1.92. And then now I can draw back the moment diagram. Take care. I have to draw it like this. Can I draw it on the original frame, please? Sorry. The moment at A is 25.2 and the tail is upwards. The moment at B, 20.1. How can I draw the moment for this number? Like the three-moment equation, can you remember? Three-moment equation. Just calculate the moment at the beginning and at the end, and then join, and then make either PL square over 8 if there was a uniform distributed load, and PL over 4 if it was a concentrated load in the middle, and PAB over L if it was a concentrated moment that it's not in the middle. But what about these two loads? It will be like this. If you need to calculate this one, it will be the same. How can I calculate this part? Anyone knows? How can I calculate this part? Assume that this is a simple beam that have 8 and 8. 9 and 9, right? Assume it's a simple beam. So what will be the reaction here? 9 and 9, right? So how can you draw bending moment? Here would be 9 times 4, I think. 36 and 36. So this will be 36. Okay. What about here BC? BC 16.2 here, and CB is 16.08. 16.08 and 16.2, and then PL square over 8. CF is 18 and 0, straight line. BD 3.9 and 1.8. 3.9 and 1.8. CE 1.92 and that's it.